everyone, and welcome to our lesson on translated exponential decay functions and the decay formula. We're first going to take a look at the translated exponential functions, what causes different types of translations to those. So let's take a look here at our list. The decay exponential function is going to look something like this. F of x equals some number to the x. And you need to know that that b, the base number for decay function, is always going to be between 0 and 1. So you might see a fraction there or a decimal. It's going to be some number between 0 and 1. And that's your clue that you're looking at a decay function, a decay picture. When you see other numbers that have been added or subtracted to this function, you need to know what changes those cause as well. So when you see that a number has been added or subtracted here with your power of x, that's going to cause your horizontal movements, left and right. When you see that a number's been added on the outside of the operation, that's going to be a vertical move, either up or down shifting. And then if you see that an additional number has been attached over with the base number, that's going to cause a stretch or a shrink. Maybe even a reflection if we see a negative there. Alright, so we're going to take a look at some examples of things we might see that have these translations applied. Alright, so the first one here, we have f of x equals 0.8 to the power of x plus 4. We can see that it is decay because it's a number between 0 and 1 as the base, and that we have a number added on the outside, which is going to cause, remember, a vertical translation. So that one would be shifted up 4 units. Another decay function in the middle here with a number subtracted on the outside, so that's actually going to shift down. All of these numbers on the outside are shifting either up or down. And then last one, we have a number added to our decay function. It doesn't matter that it's placed in the front of the operation. Anytime that it's outside of that base to the power, that's going to cause a vertical movement. So that's going to cause a shift up. All right, let's look at some horizontal translation examples. All of these you can see have the numbers added or subtracted within the operation, which means just right beside the power of x. And when that happens, we're either going to be shifting left or right. The top one is added, so that's going to be a left-hand shift of that many units, and the bottom one you can see is subtracted, so that's going to shift our function to the right. All right, and here's some examples of graphs that have been vertically stretched, one that has a stretch and one that has a shrink. We can see here that we have some numbers attached in front of that base number. The first example is a 3, and that's going to cause a stretch. It's going to sort of pull it up towards the y direction. If you can picture pulling it from the bottom and the top, you'll see in a minute on our picture on our graph. It's like if our picture was a rubber band and we could stretch it up, it would just make it a little taller up towards the y-axis. And then the bottom one here is going to be a shrink. It's going to compress it down towards the x-axis. All right, so let's take a look at the picture so we can see this more clearly. The graph of 0.5 to the power of x is shown, so we know that's the decay function. We can see on the picture that it's decreasing from left to right. And its original points, we know the y-intercept, if we were to test that and plug in a 0, we're going to get a 1. Anything to the power of 0 is 1. So it definitely goes through 0, 1. And you can test other points to see other coordinates that it'll pass through, or you can use your graphing calculator to get a very clear picture. And let's say that we need to write a new function according to these translations that are listed, and we also want to look at the picture that matches that. Okay, well, first of all, if we know that we're going to apply a translation of 4 units right, 2 units up, and a stretch by a factor of 3, let's go ahead and get that function written in there. So that's going to be f of x equals, we're still going to have our 0.5 to the x, but we're just going to add those numbers in where they're needed. Remember, the stretch factor comes first, and it needs to be situated beside our base. Okay, we need to apply a translation of 4 units right, so we're actually going to subtract 4 up here with the power Those are the ones that cause the horizontal movements. And then 2 units up, so we're going to add 2 on the outside. So there's our new function. All right, so we have that. And then if you have a graphing calculator, you can type in this whole new function and have it graph the picture. You can also test numbers to get your new coordinates by plugging in numbers for x. What's going to happen is this whole picture is going to move right 4, up 2, and it's going to be stretched by a factor of 3. When you either type that in or test your own coordinates, you're going to get a picture something like this. That new bottom line where it's leveling off, called the asymptote, is going to be at 2. We know that because it's been moved up 2 units. And we have moved all other points right 4 and up 2, and also there's some stretching. So to get a clear picture, you do want to test some values and get some coordinates there. But basically, that's the picture you're going to see. Okay, so let's talk about the formula that goes along with these types of graphs, the decay formula. We have pieces listed here, and I want you to see what everything represents, and then we're going to work on a problem that involves using this formula. All right, so when we're dealing with exponential decay, the a of t on the outside is going to represent our final amount. The little a on the inside is going to represent our initial amount, the amount we start with. The r on the inside is our rate of growth, or actually it will be rate of decay for a decay formula. And then our t here is going to represent the time that we are looking at our problem covering. All right, so let's take a look at an example. This is a good example. Let's suppose that we're buying a new car at $10,000, and we all know that cars depreciate in value. They decrease in value over time. So suppose we paid $10,000, and we know that it has a rate of decreasing by 8% each year. And we want to know how much our car will be worth in 4 years. So let's figure that out. So what we would do is we would copy in the decay formula, minus r, and raise that to the t. So we fill that in first, and now we're going to fill in our information to the pieces that we have. So we do not know final amount, a of t. We're going to leave that alone until we calculate it. We do know that we are starting at $10,000. We're going to stick that value there. Inside the parentheses, we're going to have 1 minus our rate. Now, when you're presented the rate as a percent, you want to calculate it in your calculations as the decimal version of the percent. So you always want to move the decimal over 2 spots to the left before you start calculating. So 1 minus 0.08, that's what we'll use to represent 8% in our problem. And we're looking at a time span of 4 years, so the t is 4. Okay, so following the correct order, you want to make sure that you do what's inside parentheses first. 1 minus 0.08. Raise that to the 4th power. Then you'll want to multiply by your 10,000, just following the correct order there. And when we do that, when we type all of this in, we will come up with around $7,163.93. That's how much our car will be worth in 4 years if it has this rate of decrease. So that's a real world problem looking at the exponential decay formula. So this is going to conclude our lesson on translated exponential decay functions and the exponential decay formula.